The ocean's construction crew. When Japanese bombs rained down on Pearl Harbor on December 7, 1941, the United States military faced a staggering realization that would reshape modern warfare forever. The vast Pacific Ocean, stretching over 63 million square miles, would become the theater for an unprecedented conflict. Victory wouldn't just require ships and planes and brave soldiers. It would demand something the American military didn't yet have: an army of construction workers capable of building entire military bases from nothing, often on remote coral atolls and hostile shores, sometimes even beneath the waves themselves. This is the extraordinary story of the Naval Construction Battalions, the legendary Seabees, and their most daring feats of engineering: the construction of underwater facilities that would help win World War II. The name Seabee itself was born out of necessity and clever wordplay. Officially designated as construction battalions, the initials CB were quickly adopted into the phonetic CB, a name that would become synonymous with can-do American ingenuity and determination. Their motto, Construimus Batuimus, we build, we fight, wasn't marketing hyperbole. These men wielded bulldozers and rifles with equal proficiency, building airstrips under enemy fire and harbors where none had existed before. But perhaps their most remarkable achievements were the least visible: the underwater construction projects that required them to become not just builders and soldiers, but pioneers of a new frontier. Before the Seabees, the United States Navy relied on civilian contractors for construction work. This system worked adequately during peacetime, but proved catastrophically inadequate when war erupted. Civilian contractors couldn't be ordered into combat zones. They couldn't be expected to work while under aerial bombardment or artillery fire. They couldn't carry weapons to defend themselves or their work sites. The attack on Wake Island in December 1941 illustrated this problem with tragic clarity. When Japanese forces invaded, the civilian construction workers there were unarmed, unable to fight back, and ultimately captured or killed. The military infrastructure they'd been building was left incomplete, vulnerable, useless. Rear Admiral Ben Morrill of the Navy's Bureau of Yards and Docks saw the problem clearly and proposed a solution that was radical for its time: create military construction battalions. These wouldn't be regular combat troops who occasionally built things, but highly skilled construction workers who were also trained soldiers. They would hold military rank, carry weapons, and work under military discipline. They would be able to go anywhere the Navy needed them, do any job required, and defend themselves and their work if attacked. On December 28, 1941, just 3 weeks after Pearl Harbor, the Navy Department approved Morrill's proposal. The first construction battalion recruits began arriving at training camps in January 1942. The Seabees were born. The challenge of Pacific warfare. The Pacific War presented engineering challenges unlike any conflict in human history. The European theater, while certainly demanding its own feats of military engineering, at least offered existing infrastructure. France had roads and ports and cities, even if damaged by war. Germany had the same. But the Pacific was different. The Pacific was thousands upon thousands of miles of open ocean, dotted with islands that often consisted of nothing more than coral, jungle, and hostile terrain. Many of these islands had never seen modern construction. Some had barely seen human habitation. Yet these remote specks of land would need to be transformed rapidly into fully functioning military bases, complete with airfields, harbors, fuel storage, hospitals, ammunition depots, and housing for thousands of troops. Consider the logistics alone. Every nail, every board, every bulldozer blade, every bag of cement had to be shipped thousands of miles across submarine-infested waters. Supply lines stretched from California to places most Americans had never heard of: Guadalcanal, Tulagi, Espiritu Santo, Rendova, Saipan, Tinian, Iwo Jima, Okinawa. The distances boggled the mind. From San Francisco to Guadalcanal was over 5,000 miles. From Australia to New Guinea was still over 1,500 miles of dangerous ocean. And once materials arrived, assuming they arrived at all and hadn't been sunk by Japanese submarines or diverted to higher priorities, they had to be unloaded, often onto beaches where no docks existed, and moved inland through terrain that might be swamp, jungle, or volcanic rock. The islands themselves often seemed designed to thwart construction efforts. Coral atolls, formed over millennia by tiny marine organisms, created rings of land barely above sea level. These atolls couldn't support heavy machinery without special preparation. The coral had to be crushed and compacted, a process that destroyed equipment and took enormous effort. Volcanic islands offered firmer ground, but came with their own challenges: steep terrain, dense jungle, and soil that could turn to impassable mud during tropical rains. Some islands combined the worst of both worlds. Peleliu, for instance, where some of the war's fiercest fighting occurred, was covered in a sharp, jagged coral limestone that shredded boots, destroyed equipment, and concealed an elaborate system of Japanese caves and bunkers. Temperature and weather added another layer of difficulty. The tropical Pacific wasn't a vacation paradise for these construction workers. It was a blast furnace. Temperatures regularly exceeded 100 degrees Fahrenheit with humidity to match. Men working in these conditions could become heat casualties within hours. Tropical diseases, malaria, dengue fever, dysentery, fungal infections were constant threats. A simple cut could become infected in the humid climate, potentially leading to blood poisoning or worse. Typhoons could bring winds powerful enough to flip heavy equipment and destroy months of work in hours. And then there was the enemy. Japanese forces, knowing that American advances required bases and airfields, specifically targeted construction sites. Seabees learned to work with one eye on the sky, listening for the distinctive engine sound of approaching Japanese bombers. They dug foxholes beside their bulldozers and kept rifles within arm's reach of their surveying equipment. On Guadalcanal, Seabees finished Henderson Field while Japanese ships shelled the island and Japanese planes bombed it daily. The men would work until the air raid siren sounded, scrambled to their defensive positions, fight off the attack, then return to their tractors and cement mixers to continue building. This wasn't the exception, it was routine. Birth of underwater construction capability. The challenge of underwater construction emerged almost immediately as the Pacific Campaign progressed. Traditional harbors required natural deep water or extensive dredging operations that could take months. But island-hopping warfare moved too fast for traditional approaches. Airfields needed to be operational in weeks, not months. Harbors had to handle supply ships within days of an island's capture. This urgency drove innovation, and the Seabees proved remarkably adaptable innovators. The first underwater challenge was often the simplest, getting supplies from ship to shore. Deepwater harbors were rare in the Pacific island chains. Most islands featured shallow coral reefs extending hundreds of yards offshore. Supply ships couldn't approach these beaches without ripping their hulls open on coral heads. The solution required underwater construction, pontoon causeways and piers that could be assembled rapidly and extended from the beach over the reefs to water deep enough for larger vessels. These weren't simple wooden docks. They were complex engineering projects requiring underwater survey work, coral blasting, and the installation of pilings or anchors in the seabed. Seabee divers became essential to these operations. These weren't recreational divers or pearl divers. They were construction workers who learned to apply their trades underwater, using equipment and techniques that were primitive by modern standards, but revolutionary for their time. Early Seabee divers worked with shallow water diving rigs, surface-supplied air systems consisting of a compressor on a boat or dock, air hoses, and weighted boots to keep the diver on the bottom. The diving helmets were heavy copper and brass affairs, weighing over 50 pounds and bolted to a canvas and rubber suit. A diver in full gear might carry 200 pounds of equipment, walking along the ocean floor like an astronaut on an alien world. The work was dangerous in ways both obvious and subtle. The obvious dangers included shark attacks, although these proved less common than expected. More threatening were the mundane hazards: becoming entangled in wreckage or lines, running out of air due to compressor failure or severed hoses, suffering the bends from ascending too quickly, or being struck by dropped equipment from above. In combat zones, additional hazards emerged. Japanese mines and unexploded ordnance littered many harbors. Enemy infiltrators might cut air hoses or attack divers as they surfaced. Even friendly fire posed risks. Jumpy guards sometimes shot at anything moving in the water after dark. The underwater construction techniques developed by the Seabees evolved rapidly through necessity and experimentation. Coral removal became a specialized skill. Divers would descend with pneumatic drills to bore holes in coral heads, then pack these holes with explosives. The charges were connected to waterproof firing circuits and detonated remotely. A single blast might clear a channel, or it might reveal more coral that needed removal. The process was painstaking, dangerous work. Setting explosives underwater required perfect attention to detail. A wet connection could cause a misfire. A poorly placed charge might blow a crater in the wrong place, or worse, prematurely while the diver worked. Yet Seabees became remarkably proficient, clearing entire harbors in weeks. Underwater surveys were another critical task that required divers to map the ocean floor with unprecedented accuracy. Before any harbor construction could begin, engineers needed to know the exact depth, composition, and contours of the seabed. Divers descended with weighted lines, taking depth measurements every few feet. They collected samples of the bottom material, sand, mud, coral, rock, to determine what type of foundations would be needed for piers and causeways. They mapped coral heads, underwater caves, and other obstacles. This work was tedious and time-consuming, but absolutely essential. A pier built on unstable sand might collapse under the weight of a loaded truck. A channel cleared to insufficient depth would run ships aground. The development of pontoon systems revolutionized how quickly harbors could be established. Rather than building traditional piers from pilings driven into the seabed, Seabees increasingly used floating pontoons, essentially large watertight steel boxes that could be assembled into various configurations. These pontoons could be towed to a worksite, assembled into causeways or floating docks, and anchored in place. The underwater work involved installing the anchoring systems, heavy weights, concrete blocks, or anchors driven into the seabed, connected to the floating pontoons by chains or cables. Divers had to ensure these anchors were properly set and the connections secure. A poorly anchored causeway could break free during a storm, smashing into ships or washing ashore, destroying months of work in moments.
Advanced underwater installations. As the Pacific War progressed and the Seabees gained experience, underwater construction projects became increasingly sophisticated. Simple causeways evolved into complex harbor systems. Basic underwater surveys expanded into complete submarine base facilities. The scope of what could be built beneath the waves expanded dramatically, driven by military necessity and enabled by Seabee ingenuity. One of the most remarkable developments was the construction of underwater fuel storage facilities. Fuel was the bloodline of the Pacific War. Ships, planes, and vehicles consumed enormous quantities of gasoline, diesel, and aviation fuel. This fuel had to be stored somewhere, but above-ground storage tanks presented multiple problems. They were vulnerable to enemy attack. A single bomb or artillery shell could ignite thousands of gallons of fuel. They took up valuable real estate on already crowded islands. They were difficult to camouflage and easy for Japanese reconnaissance to spot. The solution was to put fuel storage underwater. Seabee engineers designed and built underwater fuel bladders, essentially enormous rubber bags that could be filled with fuel and submerged in protected harbors or lagoons. These bladders were marvels of engineering for their time. They had to be completely watertight to prevent fuel from leaking out and water from leaking in. They needed valves and connections that could withstand saltwater corrosion and the pressure of both the water above and the fuel inside. They required systems for filling and emptying that could be operated from shore or from ships. And they had to be durable enough to survive tropical storms, tidal surges, and the constant motion of waves and currents. Installing these underwater fuel storage systems required extensive diving operations. First, divers surveyed the intended installation site, ensuring the bottom was relatively flat and free of sharp coral or rock that might puncture the bladders. Then the empty bladders were towed to position and carefully lowered. Divers descended to guide them into place and connect them to the anchoring systems that would keep them from drifting. The inlet and outlet pipes had to be connected, underwater plumbing on a scale never before attempted. These pipes ran from the bladders to shore or to floating docks where pumps could be installed. Every connection had to be tested, checked, and rechecked. A leak of aviation fuel into a harbor could contaminate the water, kill marine life, and create a fire hazard that could destroy the entire installation. The advantages of underwater fuel storage quickly became apparent. Enemy reconnaissance flights might photograph an island and see no evidence of fuel storage, even though tens of thousands of gallons sat hidden in underwater bladders. If a Japanese raid did occur, bombs and shells that would have ignited above-ground tanks harmlessly exploded in the air or splashed into the water above the submerged fuel. The bladders themselves were far more resilient than rigid steel tanks. They could flex and stretch rather than rupture. And the water surrounding them provided natural fire suppression if anything did go wrong. These underwater fuel depots became standard installations at major forward bases, from Guadalcanal to Saipan to Okinawa. Submarine support facilities needed their own specialized underwater construction. American submarines played a crucial role in the Pacific War, strangling Japanese supply lines and hunting enemy warships. But submarines required regular maintenance, repairs, and resupply, services that needed to be available at forward bases, not just at distant Pearl Harbor or the West Coast. This meant building submarine support infrastructure in newly captured harbors, often under less than ideal conditions. Submarine tenders, specialized ships that served as floating repair facilities, needed secure anchorages with precisely mapped channels deep enough to accommodate both the tender and the submarines. Seabee divers mapped these channels with obsessive detail, measuring depths, identifying underwater obstacles, and marking safe passages. They installed mooring buoys specially designed for submarines. These had to be heavy enough to hold a submarine steady even in rough water, yet positioned precisely so a submarine could tie up quickly upon arrival. The underwater cables and chains connecting these buoys to anchors on the seabed represented significant engineering challenges. They had to be strong enough to hold tons of submarine, resistant to corrosion in salt water, and flexible enough to accommodate tidal changes and wave action. Some submarine facilities required underwater power cables to provide electricity to submarines while moored. Running electrical cables underwater through a tropical harbor filled with saltwater, marine growth, and ships wasn't a task for amateurs. The cables themselves had to be heavily insulated and armored. Divers trenched them into the seabed wherever possible, covering them with sand or coral to protect against anchor strikes or propeller damage. At connection points, specialized waterproof fittings allowed the submarine to plug in without electrocuting anyone or short-circuiting the system. These underwater electrical systems were tested repeatedly before being certified safe for use. Perhaps the most ambitious underwater construction projects involved building partially submerged dry docks and repair facilities. Traditional dry docks required massive excavation and concrete work, projects that took years under peacetime conditions. The Seabees needed to create functional repair facilities in months or even weeks.
One solution was the floating dry dock, which could be towed to location and sunk into position with controlled flooding of ballast tanks. But these facilities still required extensive underwater preparation. The seabed had to be surveyed and prepared to create a level foundation. Divers worked with dredges to remove soft sediment until they reached bedrock or firm material. In some locations, they built underwater foundations by placing riprap, loose stone fill, to create a stable base. Concrete blocks, each weighing tons of weight, were lowered by crane with divers guiding them into precise positions. These blocks were often connected by underwater concrete pours, a technique that required specialized cement mixtures and underwater placement methods. The concrete had to set properly despite being submerged in salt water, a chemical and engineering challenge that Seabee engineers solved by experimentation and adaptation of new cement formulations. Once the foundation was prepared, the floating dry dock could be positioned and gradually settled into place. Divers monitored each stage of this process, ensuring the massive structure seated evenly and didn't shift position. They inspected the underwater portions of the dock, checking for damage, ensuring proper alignment, and verifying that all the systems worked correctly. The dock's pumping systems, which would remove water to float ships for repair, had intake and outlet points below the waterline. These systems had to be checked by divers to ensure no debris blocked the intakes and no leaks developed in the discharge pipes.
Living and working underwater. The daily reality of Seabee diving operations was far removed from the romance of undersea adventure. These were hard-working construction men doing dirty, dangerous jobs in an environment that tried constantly to kill them. Understanding their achievements requires understanding the conditions they worked in and the equipment they used. A typical diving operation began long before the diver entered the water. The diving team, usually consisting of a diver, a tender who managed the air hose and communication lines, and a phone talker who relayed messages to and from the diver, would arrive at the worksite and set up their equipment. The air compressor had to be checked and fueled. The air hoses had to be carefully inspected for leaks, cuts, or weak spots. The diving dress, the canvas and rubber suit, had to be examined for holes or deterioration. The copper helmet had to be polished to provide clear visibility through its small faceplate windows. Lead weights had to be assembled, front and back weights that hung from a belt, plus weighted boots that could weigh 20 pounds each. Dressing a diver was a ritual born of necessity. The diver would step into the canvas suit, working his arms and head through the openings. The collar of the suit, a heavy rubber assembly called the breastplate, was secured around the diver's chest and shoulders. The copper helmet was then lowered over the diver's head and twisted onto the breastplate with a quarter turn that engaged locking lugs, creating a watertight seal. The tender would check this seal carefully because any leak could flood the helmet, drowning the diver. The weights were added, front and back, making it nearly impossible for the diver to stand without assistance. Finally, the air hose and communication line were connected to the helmet. Communication underwater was primitive but functional. A telephone system allowed the diver to talk to the surface, but the connection was often scratchy and unreliable. Many divers preferred to use line pull signals, a code of tugs on a separate line that conveyed simple messages. One tug might mean, "I'm okay." 2 tugs, "Give me more air." 3 tugs, "Pull me up." 4 tugs, "Danger, pull me up fast." These simple signals could save lives when the telephone failed or when a diver's mouth was too full of water to speak clearly. Descending was a slow, controlled process. The diver walked into the water from a ladder or boat, moving carefully because the weight of his gear made him unstable. As the water closed over his helmet, the tender on the surface opened the air valve, ensuring a steady flow of air into the helmet. The diver continued walking down, 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 step by weighted step.
His world gradually darkened as the sunlight filtering through the water diminished with depth. His ears popped repeatedly as the pressure increased. 20 feet, 40 feet, 60 feet. At working depths of 60 to 100 feet, the water pressure was substantial, 3 to 4 times atmospheric pressure. The diver's canvas suit compressed against his body. His breathing felt labored because he was inhaling compressed air and exhaling against water pressure. Visibility underwater varied dramatically depending on location, weather, and recent activity. In clear tropical lagoons on calm days, a diver might see 50 or even 100 feet, allowing him to survey large areas and navigate effectively. But these ideal conditions were rare. More often, visibility was measured in feet or even inches. Stirred-up sediment from construction work could create what divers called black water, complete darkness where the diver couldn't see his own hands. In these conditions, every task had to be done by touch alone. Divers learned to work blind, identifying materials, tools, and connections by feel. They became experts at building mental maps of their work sites, navigating by memory and dead reckoning when vision failed. The work itself was physically exhausting. Every movement underwater required extra effort because of the resistance of the water and the weight of the equipment. Lifting a tool that weighed 5 pounds on the surface might feel like 20 pounds underwater. Turning a wrench, carrying materials, climbing a ladder, everything took more strength and more time. And the diver had to do all of this while breathing compressed air through a system that might provide just enough air to survive, never mind comfort. Many divers experienced a sensation called hard hat claustrophobia, a feeling of being trapped in the helmet and suit, unable to scratch an itch, wipe sweat from their eyes, or take a deep breath of fresh air. Experienced divers learned to manage this psychological pressure, but it never entirely went away. Duration limits were critical for diver safety. The deeper a diver went and the longer he stayed down, the more compressed air dissolved into his bloodstream. This nitrogen saturation was harmless while under pressure, but if the diver ascended too quickly, the nitrogen would come out of solution as bubbles in his blood and tissues, the condition known as decompression sickness, or the bends. Symptoms ranged from mild joint pain, called niggles by divers, to paralysis and death. To avoid the bends, divers had to follow strict time and depth limits. A diver at 100 feet might have only 25 minutes of working time before he needed to begin a slow ascent with mandatory decompression stops. These stops could last longer than the working dive itself, 10 minutes at 20 feet, 15 minutes at 10 feet, ensuring nitrogen slowly left the body. In practice, these time limits meant underwater work progressed slowly. A complex task that would take an hour on land might require multiple dives spread over days, with different divers taking turns because no single diver could stay down long enough to complete the job. Seabee diving supervisors became experts at choreographing these operations, ensuring continuous progress while keeping their divers safe. They maintained logs of every dive, depth, duration, decompression schedule, and tracked each diver's nitrogen load to prevent them from diving again too soon after a deep or long dive. Equipment failures were common and had to be anticipated. Air compressors broke down in the tropical heat, stranding divers underwater until backup compressors could be started. Air hoses developed leaks or were cut by sharp coral, by boat propellers, or occasionally by enemy action. When a diver's air supply was compromised, every second counted. Experienced tenders learned to recognize the signs: a sudden increase in air bubbles at the surface, the communication line going dead, or the simple intuition that something was wrong. They would immediately signal the standby diver to prepare for emergency descent while working to provide air through a backup hose. Divers themselves carried small emergency air bottles attached to their belts, enough for perhaps 5 minutes of air, just enough to reach the surface with a controlled emergency ascent if everything else failed. The tropical environment added unique hazards. Moray eels lived in crevices in coral and rocks, sometimes attacking divers who accidentally disturbed them. Poisonous stonefish, nearly invisible against the reef, could inject venom through even heavy boots. Jellyfish stings were common and painful, though rarely dangerous. Sea urchins with long, brittle spines easily penetrated canvas suits and caused infected wounds. And while shark attacks were less frequent than feared, they did occur. Divers learned to watch for sharks and recognize aggressive behavior. The standard defense was to stay calm and face the shark. Running, or rather swimming, only triggered pursuit. Some divers carried shark billies, clubs used to push away overly curious sharks. In rare cases, divers resorted to underwater weapons, knives, or occasionally modified firearms. Innovations in underwater technology. The Seabees weren't just users of diving equipment. They were innovators who adapted and improved underwater technology to meet military construction needs. The standard diving equipment at the war's beginning was essentially unchanged from the late 1800s. By war's end, Seabee ingenuity had produced significant advances. One critical innovation was improved air supply systems. The standard surface supply diving rig relied on reciprocating compressors that were heavy, loud, and prone to breakdown. Seabee mechanics modified these compressors for greater reliability and developed multiple backup systems. They created portable diving rigs that could be set up quickly in remote locations, consisting of smaller compressors, shorter hoses, and lightweight equipment that could be transported by landing craft or even carried by hand through jungle. These portable rigs sacrificed some capability. Divers couldn't go as deep or stay down as long, but they could be operational within hours rather than days, crucial for emergency salvage work or rapid harbor surveys. Communication systems improved dramatically through Seabee modifications. The early underwater telephones were fragile and often failed. Seabees ruggedized these systems, adding better waterproofing and more reliable connections. Some units developed visual communication systems for use in clear water. Simple hand signals evolved into more complex codes that allowed precise instructions to be conveyed without telephone systems. For night diving, which was sometimes necessary for operational security or because work schedules demanded it, Seabees experimented with underwater lighting. Early attempts used searchlights from the surface, but these often created more confusion than clarity, turning the water into a cloudy mess. Better results came from diver-mounted lights, waterproof flashlights, or even acetylene lamps in special housings that a diver could carry or attach to his helmet. Underwater tools evolved through constant experimentation. Standard hand tools worked underwater but were inefficient. Wrenches and pliers became heavier and harder to manipulate. Hammers lost their effectiveness because water resistance slowed the swing. Saws became nearly useless because water resistance prevented effective cutting strokes. Seabee ingenuity produced underwater-specific tools. Pneumatic impact wrenches, driven by compressed air, gave divers enough power to loosen bolts that human strength alone couldn't budge. Hydraulic cutting tools could shear through metal that defied saws. Pneumatic drills allowed divers to bore holes in coral and rock with relative ease. Explosive tools, small shaped charges, could cut cables, blast through wreckage, or demolish underwater obstacles with far less effort than mechanical cutting. Underwater welding became a Seabee specialty, though it was one of the most dangerous skills in an already dangerous occupation. Welding involves creating an electric arc, essentially a controlled lightning bolt, between an electrode and the metal being welded. Doing this underwater, surrounded by water that conducts electricity, and in an environment where any spark could ignite pockets of gas, required special equipment and exceptional skill. Seabee welders developed wet welding techniques, using special coated electrodes that created a bubble of gas around the weld, temporarily pushing away the water. The process was crude by modern standards, producing welds that were weaker than surface welds, but it worked well enough for many repairs and installations. For critical underwater welds, Seabees used habitat welding, a technique involving underwater chambers. These habitats were essentially watertight boxes, open at the bottom, that could be lowered over the worksite. Compressed air was pumped into the habitat, pushing out the water and creating a dry workspace around the weld. The welder could enter the habitat, do his work in relatively normal conditions, and then exit and have the habitat removed. These habitats were expensive and time-consuming to build and deploy, so they were reserved for essential welds where strength and quality were critical, such as repairing damaged dock structures or reinforcing underwater pipeline connections. Underwater photography became increasingly important for documentation and survey work. Early attempts used watertight boxes with regular cameras inside, lowered by cable with the shutter triggered remotely. These produced grainy, poorly lit images that were barely useful. Seabees experimented with better housings, closer positioning, and artificial lighting. Some photographers descended in diving gear with specially modified cameras, taking close-up images of coral formations, wreckage, or construction work. These photographs allowed engineers on the surface to study underwater sites in detail without having to dive themselves, significantly speeding up planning and problem-solving. Salvage operations drove significant innovation in underwater construction technique. The Pacific War produced countless wrecks: ships sunk by enemy action, aircraft that crashed into harbors, vehicles that rolled off causeways, and equipment that fell overboard during unloading operations. These wrecks weren't just losses of materiel. They were hazards to navigation, blocking channels and threatening to tear holes in passing ships. They had to be salvaged, raised, or at least moved out of the way. Seabee divers became expert salvagers, developing techniques that are still used today. The basic salvage technique involved sealing the wreck and displacing water with air. Divers would descend to a sunken vessel and seal all openings, hatches, portholes, holes blown in the hull. This required extensive underwater carpentry and welding work. Once sealed, air hoses would pump compressed air into the vessel, gradually displacing the water. As the vessel became lighter, it would begin to rise. Lift bags, large inflatable rubber bags attached to the wreck, could provide additional buoyancy. The process was slow and dangerous. A seal might fail, venting air and causing the vessel to sink again, possibly trapping divers working inside or underneath. Wrecks could shift unexpectedly as they began to rise, pinning divers or crushing them against the sea floor. Many salvage operations took weeks of patient, careful work.
Major underwater construction projects. Specific bases and operations showcased the full capabilities of Seabee underwater construction expertise. These projects, spread across the Pacific, demonstrated not just technical skill, but remarkable adaptability to varied conditions and challenges. Espiritu Santo in the New Hebrides, now Vanuatu, became one of the Pacific's major fleet anchorages and supply bases. When the Seabees arrived, it was a tropical island with a naturally deep harbor but minimal infrastructure. Underwater construction began immediately with extensive surveying. Divers mapped the entire harbor floor, identifying coral heads, measuring depths, and locating areas suitable for anchoring ships, submarines, and seaplanes. The coral proved extensive, requiring months of blasting operations. Diving teams worked daily, setting charges, clearing rubble, and surveying the results. They cleared multiple channels deep enough for battleships and aircraft carriers, creating a network of safe passages throughout the harbor. The scale of underwater construction at Espiritu Santo was staggering. The harbor eventually supported operations for dozens of major warships simultaneously. This required installing permanent mooring buoys anchored with massive concrete blocks on the seabed. Each block weighed several tons and had to be precisely positioned. Divers guided these blocks down and connected them to the mooring chains. They installed dozens of these moorings throughout the harbor, each capable of holding a heavy cruiser or battleship secure even in tropical storm conditions. The underwater cables connecting moorings to shore power and communication systems ran for miles along the harbor floor, installed and maintained by diving teams who worked year-round. Submarine facilities at Espiritu Santo included specialized underwater construction. The submarine anchorage required exceptional depth.
Submarines needed enough water to submerge even while moored for safety reasons. Divers surveyed and marked channels over 100 feet deep, working at the limits of safe diving depth with the equipment available. They installed specialized submarine moorings with quick-release mechanisms that allowed submarines to cast off and dive rapidly if attacked. These moorings were engineering marvels, combining strength with ease of use, and their installation required precision underwater work. The seaplane base at Espiritu Santo was another underwater construction showcase. Seaplanes, the PBY Catalinas and other flying boats, required sheltered water for takeoff and landing, plus facilities for maintenance and repair. Seabees constructed underwater ramps where seaplanes could taxi up onto platforms for maintenance. These ramps had to be smooth enough to not damage the aircraft's hull, yet strong enough to support several tons of aircraft, fuel, and equipment. Building them required underwater grading, installation of foundation materials, and precise placement of the ramp's surface. Divers checked every inch of these ramps, removing sharp coral, filling depressions, and ensuring proper drainage. Ulithi Atoll, captured in September 1944, became the Navy's secret weapon in the final push toward Japan. This coral atoll, barely known before the war, possessed one crucial advantage: an enormous lagoon over 20 miles across with depths suitable for the largest ships. Seabees transformed Ulithi into a floating city. At its peak, over 600 ships were anchored there simultaneously. The underwater construction challenges were enormous. The entire lagoon floor had to be surveyed. Divers worked for months mapping coral formations and identifying the thousands of locations where moorings would be installed. The mooring installation program at Ulithi was industrial in scale. Seabees developed assembly line techniques for mooring construction. On shore, concrete anchors were cast in standard molds, huge blocks with embedded chains and eye bolts. These were loaded onto barges, transported to predetermined locations, and lowered by crane with diving teams guiding them. The sheer number of moorings, eventually totaling over 700, required multiple diving teams working simultaneously throughout the lagoon. Coordination became critical to avoid conflicts, with different teams assigned different sectors and careful scheduling to ensure survey boats, blasting operations, and mooring installations didn't interfere with each other or with the fleet operations that continued even while construction proceeded. Ulithi's fuel storage represented the largest implementation of submerged fuel bladder technology. Enormous rubber fuel bags, each holding tens of thousands of gallons, were installed throughout the lagoon. The underwater pipeline network connecting these bladders to shore facilities and to floating fueling stations spanned miles of seabed. Installing this network required sophisticated diving operations. Pipes had to be trenched into the coral substrate to protect them from ships' anchors. Connection points needed accessible inspection hatches where divers could check for leaks or damage. The entire system had to be pressure tested repeatedly before being filled with fuel. Seabee divers spent months on this project, working dive after dive to ensure every connection was secure and every pipe properly installed. The salvage operations at Ulithi also required significant underwater work. Despite the careful survey and marking of safe anchorages, accidents happened. Ships dragged anchors during storms, colliding with each other. Aircraft crashed into the lagoon during takeoff or landing. Equipment fell overboard during loading operations. All of this wreckage had to be removed because Ulithi was too valuable as a fleet anchorage to leave hazards scattered throughout the lagoon.